Today, we're going right to the edge of what we know. We're going to explore the biggest, hairiest, unsolved problems in information theory. So let's just dive right in.
So let me start by asking you this. What if information is more than just data? I mean, we all think of information as just ones and zeros, right? The stuff that makes our digital world go round. But what if that's a totally incomplete picture? This one question, it's driving a revolution in how we understand pretty much everything.
Okay, so our journey has to start here, with the OG, classical information theory. The guy behind it all was Claude Shannon, back in the 1940s. He was basically the father of the whole field. He gave us this brilliant mathematical way to measure information, and he treated it simply as a way to reduce uncertainty. You know, this very concept became the bedrock of every text you send, every video you stream, literally all of our digital communication.
Now, Shannon's theory was, and still is, incredibly powerful. But, like it says here, that was just the first chapter. It turns out, a theory that was designed for telephone signals, way back in the 40s, it doesn't quite capture the sheer complexity of today's world, things like quantum computers, or even something as simple as the meaning of a message. And exploring those gaps, well, that's where things get really, really interesting.
So, first up, we're going to look at how we're rethinking the very foundations of the field. We're talking about looking beyond Shannon's original work to build something much, much broader.
This slide kind of lays out the core debate perfectly. On the left, you've got the classical theory. It's clean, it's simple, uncertainty is just probability, and it completely ignores what a message actually means. But now, look at the right, the new frontiers. They're tackling all these other kinds of uncertainty. And crucially, they're trying to bring in semantics, the actual meaning and the impact of a message. They're even working to define information as a real physical quantity, just like energy or mass. Wild stuff.
And listen, this isn't just talk. Researchers are actively developing entirely new frameworks to plug these gaps. We're talking brand new theories of uncertainty, models that can actually account for what a message means. The key takeaway here is that they're basically rebuilding information theory from the ground up.
Okay, next up, the quantum puzzle. Now, if the classical world had some gaps, the quantum world just blows the doors wide open. In this realm, the fundamental rules of information that we all take for granted, they just sort of break. So think about it like a pipe, okay? In our normal, classical world, a pipe has a fixed width. It can carry a certain amount of water, and that's it. Shannon proved that every communications channel, whether it's a fiber optic cable or a radio wave, has one single, well-defined capacity. Simple, right? Well, welcome to the quantum world. Here, that simple idea of capacity just becomes a complete mess. For a single quantum channel, scientists have come up with at least 4 competing different definitions for its capacity. We still have no idea which one is right, or if there's another one just waiting to be discovered. The scale of the challenge here is just massive. And solving these problems isn't just for kicks. It's not just academic. It's fundamental to everything, from figuring out a channel's true capacity to, and this is the urgent one, building security systems that can actually defend us against future quantum computers.
Okay, let's bring this back from the quantum haze for a second, back to the tangible world, to the tech we use every single day. Because these big theoretical puzzles, they have very direct and very stubborn consequences for coding, for cryptography, and for signal processing.
Just look at this number. Over 40 years. 40. That's how long researchers have been stuck on a single problem. Basically, figuring out the best way to combine signals from multiple sources. A 40-year roadblock, that just shows you how deep and how difficult these real-world riddles can be. And that problem is definitely not alone. This table shows just a few of the major roadblocks we're facing. In coding theory, for instance, we still don't have a formula for the capacity of a simple deletion channel. That's where bits of data just vanish. Solving that would be absolutely huge for data integrity. We're also still chasing the dream of a truly universal compression algorithm. And in cryptography, designing perfectly efficient and secure block ciphers is still an open challenge. And right here, this is one of the holy grails in modern cryptography, creating secure multilinear maps. The best way to think of them is like a cryptographic Swiss Army knife. It's a tool that could unlock powerful new types of encryption that we can barely even imagine today. Cracking this one would fundamentally change digital security as we know it.
All right, for our last section, let's zoom all the way out. Because maybe the biggest revelation of all is that information theory isn't just about computers and cybersecurity anymore. It's becoming a fundamental language for describing the universe itself.
I mean, just look at this.
The concepts of information, entropy, capacity, they're being used to unlock secrets in fields that seem totally unrelated. Biologists use it to understand the code of life in our DNA. In AI, it's totally central to how machines learn. It's being applied to game theory, to economics, even to fundamental physics. Information is like this common thread weaving through all these incredibly complex systems.
This quote, which is about a famous puzzle called the Cadison-Singer problem, it just says it all. It started as this really abstract math problem, but it turns out that solving it would be the same as solving major open questions in a whole bunch of other fields. It's just a beautiful example of how interconnected all of this really is. A breakthrough in one area can literally cause a domino effect of progress everywhere else.
And really, that's the ultimate takeaway here. This isn't just about getting faster downloads or having better security. The quest to solve the great unsolved problems of information theory, it's really a quest to understand complexity itself, whether that's the complexity of an AI's logic, a living cell, or a financial market.
So, we'll end with this question. Information theory already gave us the entire digital world. What happens when we finally solve its deepest, most fundamental puzzles? What new technologies, what new kinds of understanding are we gonna unlock? We don't have the answer yet, but man, it is going to be exciting to find out.